I've created a new learning module for you for Chapter 9. It's just like all the others, has example problems in it, it's got this presentation, it's got your homework assignments and so forth, as well as a quiz. So make sure you check that out. But this is finally the chapter where we get to start studying power cycles. And power cycles are where things typically start to come together for students. Now at first, it'll seem a little challenging because what we're doing is we're using all the information we've developed so far from Chapter 1 all the way through Chapter 7 to finally apply that knowledge to real engines, or something as an approximation of a real engine. Now, power cycles themselves are just thermodynamic cycles that consist of several different processes that together make up a cycle where the system comes back to where it started. Power cycles can be broken down into two primary categories. There are power cycles whose working fluid is just a gas, so the working fluid is just the fluid that's flowing through the engine and actually pushes applies a force to a distance. If you think about the air on top of the piston in your car, it gets hot, right, because you burn fuel in it, and then that gas, that air, literally pushes the piston down. So since it applies a force to a distance, we call it the working fluid. There are also engines that use a working fluid that moves back and forth between its gas and liquid phases. So you don't have one under the hood of your car. You might if you were riding around in a Stanley steamer, or if you were being pulled by a steam locomotive. Then that would be a power cycle where the engine is based on a working fluid, in that case water, that goes back and forth between the gas and the liquid states or phases. Now, another way of looking at power cycles is as either open or closed cycles. And the differentiation there is that an open cycle is a cycle where the working fluid is brought into the engine, it's used to do work, and then rejected out or pushed out into the atmosphere. Whereas in a closed cycle, the working fluid remains inside of the machine and is reused over and over again. Now, with an open system, you typically have, with an open cycle, you typically have internal combustion. So there's combustion of the fuel, the chemical energy that generates the thermal energy, in order to push the engine and do work inside of the engine. Whereas in a closed power cycle, it's much more common there to have external combustion, because if the cycle is closed, where the working fluid doesn't have the opportunity to somehow get back where it started, how can you have combustion in it, right? Because if you have combustion in the working fluid, well, then that combustion is going to change the properties and the nature of the fluid itself. So one thing that does confuse students along the way, for example, in open systems, is that, I keep messing that up, I'm sorry, it's open cycles. With open cycles, we typically analyze them using closed systems, and that's what's confusing about it. But if you think about it, it makes sense. The idea behind the open power cycle is that in the real engine, the working fluid moves through the engine and comes out the other side. Now, when we idealize those engines, we'll neglect the air intake and exhaust portions, because the whole purpose of that portion is really just to regenerate the working fluid. And what we'll do is assume that the fluid just stays inside of the piston cylinder device and that the piston cylinder device just remains closed. So we'll analyze it using closed system energy balances and so forth. Whereas with the closed system, or the closed cycle, we'll analyze each of the pieces, like the pump and the boiler and the turbine and the condenser. We'll analyze all those as open systems. In other words, mass is allowed to flow through each of those pieces of equipment. Now, it doesn't leave the cycle as a whole or the machine as a whole, but it does flow from one piece of equipment to the next. So finally, we get to study engines, and we get to apply what we've learned so far, that we've worked so hard so far with in thermo from chapters 1 through 7. We get to apply all of this stuff to real engines, which is kind of good and kind of scary, right? Because if you look at these two cutaways, you'll probably recognize the piston cylinder device on the left, but you probably will not recognize the gas turbine engine on the right. This is a gas turbine engine that was developed by Chrysler back in the 60s and 70s, and I really wish we still were developing it today. I really think that we could do some interesting things with it. It was an interesting engine because it could run on perfume, it could run on kerosene, it could run on diesel, gasoline, all sorts of things. And so I like the idea of having a engine that's fuel flexible. Of course, that's kind of where we're going today with flex fueled vehicles. But anyway, I think with the computer control we have today and the upgraded sensor technology and so forth, I think we could do a lot better with gas turbine engines in cars. But piston engines have had so much development, it'd be hard to catch up to them. Anyway, looking at these engines, analyzing either one of them seems like quite a daunting task because there's so much there, right? There's so much detail and so much to know. Well, that's where idealization comes in. If you were, let's say you didn't know anything about baking potatoes and you didn't know if you should set the oven on and put the potato in the oven for 5 seconds, 5 minutes, 5 hours, 5 years, right? You have no idea how long it will take to bake a potato. How could you calculate how long it should take? Well, if you knew that you had to get the center temperature of the potato up to a particular level so that the potato were fully baked, then you might say, well, I remember 220 and I remember transient heat transfer. I remember there was this model of a sphere. What if I look at this potato and say, you know, it's roughly round and it's made up of, well, it's got a lot of water in it. That's one of the main components the potato has. So couldn't I pretend that this potato was just a sphere of water and calculate, given an oven temperature, how long it would take the center of that water sphere to come up to the temperature required for the potato to be baked? Right, that would be one way of doing it. Now, is the potato actually a sphere of water? Obviously not, right? You put it in the oven, it doesn't just fall apart. But its properties are reasonably close to those of a sphere, and you could, assume a reasonable diameter sphere and approximate how long it would take, and at least get in the ballpark of how long it would take for the potato to bake. And you'd find that it'd be, on the order of an hour or so at normal temperatures. Now, that gives you a much better idea than 5 seconds, 5 minutes, a year. It gives you a much better idea of how long it would take. And so in the same way, what we're going to do is we're going to take real cycles and we're going to idealize them. We're going to make some assumptions about them, make some approximations along the way. And what we'll do is get at sort of the details of what parameters make a difference. How would we vary those parameters to increase the performance of the engine? So we're not analyzing real engines, we're analyzing idealizations of real engines. So what about the Carnot cycle? Because that was one of the first cycles that we saw. In fact, it is the first cycle that we saw. What are we doing with it? Well, basically what we're doing is we're building on it to generate some other cycles, some cycles that will more closely resemble or model the behavior of real engines, better than the Carnot cycle can do. Remember, the Carnot cycle was a fully reversible cycle. Well, the ideal cycles that we're going to develop for various types of engines will be fairly good for their engine type, but will be closer in reality than the Carnot cycle. So we'll have a cycle that is relatively close for the operation of jet engines, for gas turbine engines, such as is used in a lot of helicopters or the M1 Abrams tank. We'll have a diesel cycle that will be our model for an average compression type ignition engine, or an Otto cycle, which is probably what you use. Now notice that's not AUTO, it's OTTO cycle, named after the man that developed the cycle. But anyway, the gasoline engine that you use is a spark ignition engine, and the Otto cycle is a model of spark ignition type engines. We'll also see the Stirling cycle, which you haven't seen yet. Turns out the Stirling cycle is actually a fully reversible cycle as well, and so it ends up with the same efficiency as the Carnot cycle. So basically what we're doing is moving from the Carnot cycle, which is a very highly idealized kind of limit, the best we can ever do, all closer to the real world through these cycles by using other cycles than just the Carnot cycle. But what good was the Carnot cycle? What did it teach us? Well, it still taught us a very important principle. It taught us that these heat engines, that all of their goal is to take thermal energy and convert it to work and reject then the waste thermal energy through heat to a sink. What the Carnot cycle taught us is that the farther we can get those two reservoirs of thermal energy apart, the higher the temperature of the high reservoir and the lower the temperature of the low temperature reservoir, the more efficient the engine can be in general. Now, obviously there are limitations. You can't just give an engine the highest temperature you can make, because you could melt the engine. You can damage the engine, and then it's no longer useful as an engine. So the Carnot cycle was useful. It gives us sort of a general guide. But these other cycles that we're going to develop will give us a little bit more detail about how to improve the performance of these various types of engines. So what would those look like? Well, the first thing we have to do before we can look at any of the cycles is describe what's called the air standard assumptions. Now, the air standard assumptions are just concentrating on the working fluid itself and how the working fluid, the nature of the working fluid and what it does. So there's a few assumptions we're going to make. One is that the working fluid is air and not air mixed with fuel or burnt fuel in the air, not combustion products. Now, that may seem like a pretty far stretch, but if you think about the way that the engine actually works, think of the engine in your car, for example, what do? Well, you put air, pardon me, you put air in the cylinder and you put fuel in the cylinder. Well, any idea how much? Well, yeah, the stoichiometric ratio is around 14:1 or so for gasoline. What that means is that you're putting 14 times the mass of air versus mass of fuel into the combustion chamber for that particular power stroke. And so there's a lot more air in the system, and by the way, air, of course, is made up primarily of nitrogen, right? It's 79% nitrogen, which by and large does not participate in the chemical reaction where the fuel is being burned. And so with reasonable accuracy, you could say that hot nitrogen is what pushes your car down the road, because that's really the purpose of the oxygen and the fuel, at least from the engine's perspective, is to heat up the nitrogen so that the nitrogen will have a lot of thermal energy and can expand doing work pushing the boundary of the piston. So it's not really such a bad assumption to just pretend that the working fluid that's actually pushing the piston down is just air, because that's basically what it is. Also, we will assume that that air behaves ideally, which is not a bad approximation at all. Another assumption we'll make is that all of the processes in the cycle are at least internally reversible. Now, not fully reversible like the Carnot cycle. Like I said, we're getting a little bit closer to reality, but they are at least internally reversible. The next assumption is that instead of putting air and fuel into the combustion chamber and literally burning the fuel, we're going to assume that the air in the combustion chamber, well, that there's no combustion at all, and the heat is simply transferred to it, thus increasing the thermal energy of the air, just like the purpose of the fuel. And so instead of having, you know, a combustion process, we'll have a heat addition process. Similarly, in a real engine, when the gases have finished pushing the piston down on the power stroke, an exhaust valve opens up and the piston pushes out the exhaust gases out the tailpipe or out the exhaust header. And then that valve closes and the intake valve opens and the piston moves down, allowing air to flow in along with fuel for the next round. Now, instead of having that process occur, we're going to assume that the air remains in the cylinder. There's no opening and closing of any valves. And instead, thermal energy is simply extracted from the air by heat. So heat flows out of the air and out of the system. So basically, the combustion and the exhaust processes are replaced by a heat addition and a heat rejection, respectively, process. Now, we can add to this, and sometimes we'll use what's called the cold air standard assumption, and that already takes into account all four of these air standard assumptions, but adds one more to it, and that addition is that the air has a constant heat capacity, both CV and CP, and that we simply take the heat capacity of the air to be those values at room temperature. So these are the air standard assumptions that we will use in analyzing our engines, and because most of the engines we deal with will have air as their working fluid.